Usually when we talk about a medical diagnosis, there's this expectation of precision.
Right, absolutely.
Like you break your arm, the x-ray shows that jagged white line in your radius, and the doctor just points at the film and says, there it is.
Broken or not broken.
Exactly. It's clean, it's visible, and honestly, it's incredibly comforting to just know. But I want you to imagine if that x-ray machine was, I don't know, programmed to lie to you.
That is a terrifying thought.
Right. Imagine stepping into the world of industrial manufacturing, where perfectly good, physically indestructible heavy metal machines are being deliberately murdered by their own brains.
Yeah, it's essentially a hostage situation.
It is. The machine isn't actually broken, but the software is holding the iron hostage. It throws up these catastrophic error codes and basically demands a ransom.
It is the absolute definition of diagnostic muddy waters.
Yeah.
And we're looking at a massive hidden crisis in global manufacturing.
Millions of dollars in capital assets, right?
Oh, easily. Stranded on factory floors, essentially held hostage by invisible lines of code.
So, welcome to today's deep dive. We are exploring these hidden software toll booths controlling global industry. We're going to look at why machines that could easily, cut aerospace-grade steel for another 30 years are being forced into early graves.
And we're going to talk about the people fighting back.
Yes, the renegade engineers who are breaking the locks, decoding these encrypted handshakes, and rescuing this equipment. To guide us, we have a really fascinating stack of sources today.
The contrast in the sources is what I love here.
Same. On the ground level, we have raw technical data. Repair logs, service catalogs, fault code libraries from a company called Synchronix Electronics in India.
They're literally in the trenches doing component-level repairs on thousands of these industrial controllers.
Yeah, getting their hands dirty. And then on the macro level, we have these deeply strategic, almost philosophical essays from a source identifying themselves as the quiet architect.
Which is such a great name, by the way.
It really is. This is an engineer who builds bioprinters today, but actually started out putting robots into grenade factories.
A wild career trajectory.
Completely wild. So, okay, let's unpack this. We need to start by looking at what is physically sitting on these factory floors. Because if you picture heavy manufacturing, you picture iron.
Right. Lathes, milling machines, ball screws, heavy linear guide rails.
Exactly. And from what our sources tell us, the physical iron of a computer numerical control, or CNC machine, is practically indestructible.
Yeah, the foundational premise here really requires us to completely separate the mechanical body of the machine from its digital brain.
Okay, separate the body and the brain.
Right. A CNC machine is essentially a kinematic linkage driven by servo motors. The mathematical physics of moving a piece of metal along an X, Y, or Z axis with extreme precision.
We're talking down to the micron here, right?
Down to the micron. It's a solved problem. We know how to do it. The cast iron beds, the linear rails, these physical components retain their tolerance capabilities for decades.
They don't just suddenly forget how to cut steel.
No, they absolutely do not.
But they do suddenly stop working. And it's not because the ball screw wore out. It's because of this concept called the legacy OEM handshake protocol.
The artificial bottleneck.
Right. So what is the mechanism behind this bottleneck? Because from a business standpoint, putting a synthetic toll booth in the middle of a perfectly functional machine seems, I don't know, almost hostile.
Well, it is hostile. But the bottleneck isn't a failure of engineering at all. It's a triumph of a very specific, very aggressive business model.
Okay, walk us through that.
So legacy original equipment manufacturers, the OEMs.
These are the massive companies, right? Like Fanuc and Siemens.
Exactly, the giants. They design their control software to act as a barrier. They impose an artificial abstraction layer over the actual physics of the machine.
So the machine can do the work physically, but the software won't let it.
Exactly. The kinematic precision is locked behind proprietary SRAM parameter configurations.
SRAM. That stands for static random access memory, right?
You got it. It's volatile memory. It holds the machine's configuration data, its tool offsets, its coordinates, and the OEM controllers run this constant, encrypted, cryptographic handshake between the software brain and the hardware body.
Like a secret password being passed back and forth?
Exactly. The software sends a heavily encrypted ping to the motor drive, essentially asking, hey, do you have the correct cryptographic key? Are you authorized by the manufacturer?
So it sounds like Okay, imagine moving into a house you bought, but the builder kept the master key.
Oh, that's a good way to put it.
Right, like the plumbing works, the electricity is perfectly wired, but every time you try to turn on the kitchen lights, the house checks a server to see if the original builder is physically holding the switch.
Yeah, if you try to bypass that switch,
Let's say you're an MSME, right?
yeah,
A micro, small, and medium enterprise operator. You're just trying to upgrade your older machine with a modern open source controller.
if you do that, the house literally burns itself down.
Wait, really? It just destroys itself?
That analogy captures the mechanism perfectly. The moment the legacy system detects that the proprietary handshake protocol has been bypassed, or honestly even just interrupted, it reacts with a highly aggressive failure state.
It doesn't just pop up a polite warning on the screen like, hey, unauthorized hardware detected.
Oh no, no polite warnings. It intentionally wipes the internal SRAM memory. It triggers a fatal system alarm that completely bricks the production asset.
So the machine becomes a massive, multi-ton, useless paperweight.
Exactly. They weaponize safety to enforce hardware obsolescence. As long as the operator believes the machine is mechanically broken, the OEM wins.
Because they maintain an absolute capital expenditure monopoly.
Bingo. If the machine breaks, you are forced into a wildly expensive OEM service contract to get it running again.
Or worse, you have to scrap the perfectly good iron and buy an entirely new machine from them.
Right. The control point sits firmly with those legacy control manufacturers. The physical asset is treated as nothing more than a hostage to the software permissions.
Obscurity protects incumbents.
And this enforced obscurity is immensely profitable.
So put yourself in the shoes of the factory owner. Imagine you're the factory owner in this situation, right? You've got a deadline. You need to ship aerospace parts tomorrow morning.
The pressure is on.
Suddenly, the floor goes quiet. You walk out there, and your $1 million machine is just sitting idle with a blank screen. You are bleeding what our sources call lakhs of rupees.
Hundreds of thousands of rupees.
By the hour, in completely unplanned downtime. What is your very first move? Like, what does this hostage situation actually look like on the diagnostic level?
Well, the Synchronix Electronics technical catalog is incredibly illuminating here because they are the ones actually walking onto that silent factory floor.
The emergency responders.
Basically, yeah.
Yeah.
And it is rarely, a dramatic explosion or a smoking motor. It is silent and it is catastrophic.
Just a blank screen?
A blank screen, wipe tool offset tables, lost work coordinates, and it's usually accompanied by these really cryptic fault codes.
Like what? What are we looking for?
Take the Funnick ecosystem, for example. When that encrypted handshake fails, or if the system detects an unauthorized anomaly, it throws an alarm like PS00000091.
Okay, I actually have the logs for PS000 in front of me. It classifies it as a ROM or RAM parity error. It mentions EEPROM data corruption.
Right.
But how does an EEPROM physically hold memory? And how does the OM software actually trigger a wipe? Because, memory doesn't just vanish into thin air, right?
It doesn't. So an EEPROM is an erasable, programmable, read-only memory chip. It physically stores data using these microscopic arrays of floating gate transistors.
Okay, floating gate transistors.
Yeah, these gates trap electrons. And the presence or absence of those trapped electrons dictates the ones and zeros of the machine's code.
So it's physical.
Very physical. In a normal operating state, this data is perfectly stable. But when the controller's security protocol is tripped...
Like if it detects an unauthorized logic board connected to the bus.
Exactly. When that happens, the software executes a deliberate instruction to alter the voltage routed to those specific memory addresses.
It fries it.
It floods the gates. It scrambles the trapped electrons, or it severs the connection to the backup battery, maintaining the SRAM state.
Oh, wow.
The voltage drops, the electrons dissipate, and the brain is totally wiped. The data corruption isn't an accident, it is an engineered execution.
That is incredibly aggressive.
Very.
And then we have alarms like SV0401 on the phonics side. The logs call it an access card servo alarm, specifically noting VRDY off.
VRDY, yeah. Velocity ready.
It looks like the system is literally refusing to send a ready signal to the motor. Like the software is consciously cutting the electrical connection between the brain and the arm.
That's exactly what's happening. And the whole sequence takes milliseconds.
Milliseconds.
Yeah. The microprocessor on the main board sends the command ping to the servo amplifier. The amplifier is the hardware that actually supplies the high voltage to the motors.
Okay.
The amplifier expects that encrypted handshake key. If the system has been tampered with, the cryptographic key fails.
And the software just cuts the cord?
Immediately. It registers the failure. drops the velocity-ready signal down to 0 volts, and physically opens a relay that cuts power to the motor drive.
Boom. Paralyzed.
Paralyzed. And over on the Siemens side, you see very similar mechanisms with their 700 OCAX series alarms, like 7013 down.
I see that one. A drive SLEQ bus error.
Right. That's a communication error on Siemens' proprietary drive SLEQ network. To the operator standing there, the spindle just refuses to rotate.
It just gives up.
Yep. There's a following error, meaning the physical position of the tool is no longer matching the commanded position in the software because the communication has been totally severed.
So the machine just sits there, mechanically totally sound, but completely paralyzed.
Exactly.
So to negotiate with this hostage taker, you obviously can't just walk up with a wrench.
Definitely not.
What is the diagnostic arsenal required to safely retrofit or repair these machines before anyone even thinks about making a board-level change?
It's intense. The tools listed in the Synchronix logs represent deeply sophisticated electrical engineering. You need oscilloscopes to visualize the electrical sine waves and voltage drops.
Okay, oscilloscopes.
And you need logic analyzers to capture the actual ones and zeros, mapping the hexadecimal communication across the data bus to see exactly where the cryptographic handshake is failing.
Now wait, the logs also mention tools that sound almost ancient to me. PCM-CIA cards, compact flash cards, RS-232 serial cables.
Yeah, the legacy stuff.
If this is such high-level, sophisticated diagnostic work, why are they using data interfaces from the 1990s?
That's a great question. It's because industrial equipment prioritizes noise immunity and stability over pure speed.
Noise immunity.
Yeah. A factory floor is incredibly electrically noisy. You have massive motors turning on and off, high-frequency welding happening nearby.
Oh, sure. So a modern cable would just get scrambled.
Instantly. An RS-232 serial connection pushes a massive plus or minus 12 to 15 volts just to signal a single 1 or a 0. It's incredibly robust.
It just bulldozes through the interference.
It punches right through the electromagnetic interference that would, instantly scramble a modern USB connection.
That makes total sense.
So the engineers use these legacy interfaces because they are literally the only reliable way to interface directly with the core memory of older Fanuc and Siemens boards to attempt data preservation before the system wipes itself.
Got it. And when a physical component on the board actually is blown, they use BGA rework stations, right?
Yes. Ball grid array.
That's a method where the microprocessor connects to the board, not with visible pins, but with a grid of tiny microscopic solder balls hidden completely underneath the chip itself.
Yet you cannot solder that by hand.
Yeah.
It's impossible.
I would imagine not.
You require highly controlled thermal rework stations with very precise temperature profiles. You have to heat the entire board to a specific ambient temperature, then use targeted infrared heat to melt those hidden solder balls simultaneously.
Without warping the fiberglass board or frying the adjacent components.
Exactly. It's an art form. And once that chip is replaced, they don't just test it with a standard multimeter. No.
No, they hook it up to dedicated CNC test benches equipped with actual physical Fanuc and Siemens servo motors to simulate closed-loop operation.
But hold on a second. If these OEMs are claiming this memory wiping and system paralysis is a built-in safety feature.
Right, the safety argument.
Yeah. Doesn't hacking into a giant steel-cutting machine with an open-source AI sound incredibly dangerous? Aren't these independent engineers bypassing the exact guardrails meant to keep workers safe? Like, if you screw up the BGA rework or the handshake spoofing, couldn't a 500-pound metal arm just swing wildly out of control?
See, that is the exact narrative the legacy manufacturers want operators to believe. It's fear-mongering.
So it's not true.
We have to clarify the difference between true mechanical safety and artificial software modes.
Okay, break that down for us.
True mechanical safety involves physical barriers, light curtains, and hardwired emergency stop chains that physically cut power regardless of what the software is doing.
Like a physical kill switch. Exactly. What the OEMs are protecting with these encrypted SRAM handshakes is not human safety. It is their intellectual property and their service revenue.
Ah.
The proof that independent repairs are deeply systematic and not just reckless hacking is detailed in the 6-step Synchronix repair process.
Walk us through those 6 steps because the level of discipline here is wild. I mean, it's meticulous.
It really is. Step 1 is meticulous logging. They receive the board and document every single physical anomaly and fault history. They don't even touch a soldering iron yet.
Total visual inspection first.
Right. Step 2 is the program backup attempt using those RS-232 cables we talked about. Program preservation is the absolute top priority here.
Because if they lose the parameters, it's game over.
Yeah, if they lose the proprietary machine parameters, the board is completely useless even if it's physically repaired.
Right. Okay, step 3.
Step 3 is main board diagnosis using the logic analyzers. And they aren't guessing here. They are comparing the signals coming off the damaged board against huge libraries of reference waveforms from known good machines.
So they know exactly what a healthy cryptographic ping should look like on an oscilloscope.
Exactly. They know what normal looks like.
And then step 4 is the axis and spindle card test on those physical simulation benches we talked about, right?
Correct. Simulating the real world. Step 5 is the actual component-level repair using the BGA rework stations and original spec components.
And finally, step 6.
Step 6 is the final simulation and dispatch, running the board under full electrical load for hours before it ever goes back to a client. It is rigorous, highly disciplined engineering.
It's a highly legible, completely controlled process.
Yes. The goal is to restore the machine's functionality and its intrinsic mechanical safety without being beholden to the original manufacturer's synthetic toll booth.
Which brings us to the actual heist.
The fun part.
The really fun part. How are these independent engineering teams mapping the proprietary SRAM parameters to decouple the mechanical hardware from the OEM software?
It's brilliant.
Our sources highlight independent MSME engineering teams in regions like Rajkot and Pune in India. They call them Jugaad to precision retrofits.
Jugaad, yeah.
Jugaad is roughly translated as a flexible, innovative hack, right? But applied here to sub-micron precision manufacturing.
Exactly.
So picture an older Fanuc i0i controller, and it's slated for the scrapyard. An operator walks up and physically clamps a logic analyzer directly onto the machine's data bus.
Imagine a dense anodized aluminum block with these matte black silicone cables ending in dozens of exposed, gold-plated microclips.
Sounds intense.
The engineer carefully hooks these clips directly onto the exposed pins of the microprocessor on the weathered green fiberglass of the old circuit board. They're tapping directly into the nervous system of the machine.
But they don't try to force the machine to talk, right? They just wait.
They wait.
They initiate a standard automated tool change sequence. But why tool change? Why not just jog the machine left or right or, turn the spindle on and off?
Because a simple movement like jogging doesn't require a complex security handshake. But an automated tool change is a massive kinematic ballet.
A kinematic ballet, I like that.
It requires the z-axis to retract to a highly specific, mathematically perfect machine coordinate. It requires the spindle to orient and lock its rotation perfectly. It requires the tool carousel motor to swing into position.
It's a lot of moving parts all at once.
Exactly. It is a highly coordinated event that forces the machine's brain to communicate extensively with its body. It forces the controller to transmit the most heavily encrypted kinematic instructions in SRAM parameters.
Ah.
The controller has to verify every single coordinate and authorization key simultaneously.
So it creates a massive data burst.
Huge.
It forces the proprietary handshake out into the open bus, and the logic analyzer is just sitting there recording the entire conversation.
Yep. The amber LEDs on the analyzer are just blinking furiously as it intercepts all those hexadecimal codes.
So it's basically a digital wiretap. They record the secret password being whispered between the brain and the arm during that tool change.
That's a perfect analogy.
And once they capture that data burst, they map the exact sequence of the handshake.
Right. And then the decoupling begins.
How does that work?
They deploy a secondary open-source edge AI device, usually a small, incredibly powerful industrial microcomputer, and they program it to spoof the mapped commands.
Spoofing the handshake.
Exactly. They wire this edge device between the legacy controller and the physical servo amplifiers.
Okay, so when the OEM software sends its encrypted ping asking, "Are you authorized?" the Ed AI instantly replies with the exact perfect hexadecimal string it recorded earlier.
Yes.
The OEM software thinks everything is fine.
It's totally fooled. It never triggers the fatal system alarm. It never drops the voltage to wipe the memory.
The machine's internal defense mechanisms are just completely pacified.
Exactly. Meanwhile, the open-source Edge AI takes total control of the mechanical hardware. It bypasses the bottleneck entirely. The indestructible metal body is completely separated from the artificially limited software. The factory owner regains total control of the asset.
That is, I mean, it's incredible. But if I'm a startup founder listening to this, I am used to thinking of business risk as, running out of funding or a competitor launching a faster app.
Right, the usual startup risks.
But the Quiet Architect sources frame this entire logic analyzer heist strictly as an essential corporate strategy for risk mitigation.
Yes, they do.
This suggests the real hidden risk is buying a factory full of machines you don't actually control. Do founders usually just accept that the manufacturer owns the machine forever?
It is an incredibly common blind spot, especially for founders moving from the software world into physical manufacturing.
I can see that.
The Quiet Architect notes that process failures hide behind optimistic dashboards.
Oh, optimistic dashboard.
Yeah, a founder looks at a sleek, cloud-connected interface showing green check marks across the factory floor and assumes they have operational control.
But they don't.
Not really, because governance arriving late is incredibly expensive. Great products fail because the founder never actually owned the control point on the physical floor.
Give me an example.
Well, if Siemens pushes a firmware update that inadvertently bricks a legacy controller on your critical path, your sleek dashboard turns red and you have zero recourse.
You're just dead in the water.
Get in the water.
So how does a founder audit these hidden workflows before they scale? The sources outline a very specific 48-hour validation plan. And they obviously don't advise, ripping apart the main production line on a Tuesday afternoon.
Right, definitely don't do that. The validation plan is designed as a highly structured asymmetric bet.
Okay, step one.
Step 1. Identify an older generation controller, like a Fanuc Zero-i, that is already slated for decommissioning. It's sitting in the corner, maybe destined for scrap.
Right. Using a decommissioned machine completely removes the operational risk.
Exactly. If you make a mistake and the machine wipes its memory, it doesn't impact production. You were going to scrap it anyway.
Smart. Step 2.
Step 2. Execute a 30-day litmus test compressed into a 48-hour window. You bring in an independent engineering team. You attach the logic analyzer during the tool change, just as we discussed.
All right, do the wiretap.
Yep. Step 3. Intercept the bus and prove that the kinematic commands can be spoofed.
But the goal isn't to run a full production part, right?
No. The goal is just to prove you can capture the SRAM parameters and feed them back via an edge device to move a single axis safely.
Oh, just one axis.
Yeah. If you can move the z-axis just 1 inch using an open-source brain, you have mathematically proven that the OEM moat can be breached.
That's fascinating.
By treating legacy hardware as a dumb kinematic body, just a collection of raw actuators and indestructible iron founders, audit their dependencies. They ensure they own their outcomes rather than relying entirely on OEM service contracts.
But proving you own the hardware in a 48-hour test isn't just about an engineering victory. The second you realize you don't need the OEM, the entire economics of your manufacturing floor completely flips upside down.
Totally flips.
Yeah. You are no longer staring down a $3 million capital expenditure upgrade every 5 years just because Fanuc decides to stop supporting a specific circuit board. The budget gravity shifts.
We are looking at the inevitable consequence of a system becoming highly legible.
Legible!
Yeah. When a previously obscure bottleneck, like the proprietary handshake, is decoded, the power dynamics shift violently. The massive capital expenditure budget just evaporates.
So where does the money go?
Instead of buying new OEM hardware, the budget moves to surgical, highly targeted software retrofits using cheap, powerful edge AI.
And this creates entirely new power players. Independent service teams, like those engineers in Pune with their logic analyzers and oscilloscopes, suddenly hold a massive asymmetric advantage. They are shifting the choke point.
Absolutely. The control point used to be the proprietary programmable logic controller, the PLC.
Locked in a steel cabinet and guarded by the OEM.
Exactly. If you control the PLC, you control the factory. But now the choke point has shifted entirely toward open source edge AI kinematics.
The guys with the logic analyzers.
Right. The independent teams offering protocol bypass services are essentially democratizing heavy industry.
That's huge for the smaller shops.
The MSMEs win more than linearly here. Their overhead for capital equipment drops by an order of magnitude. It allows a small shop in Rajkot to compete on precision and output with massive, heavily funded corporations.
It's a brilliant underdog reality. But, the author of our strategic sources, The Quiet Architect, insists this isn't just about factory economics.
Oh, it goes way deeper.
Or sticking it to legacy monopolies. They argue this specific type of rebellious engineering is fundamentally about humanity.
Yes.
And to understand that, we have to look at the foundational story they share about the grenade factory.
It is a stark, grounding narrative. It really elevates the technical details into something profound.
Tell us the story.
So the author describes their early career, observing workers in a munitions plant handling live explosives on an assembly line. And what stood out wasn't the efficiency of the line, but the physical tension. The workers were moving as if they were holding their breath.
Wow.
Fear was the primary dictator of the workflow. The entire environment was built around the terrifying physical risk of sudden catastrophic failure.
So the author didn't just suggest, better safety goggles.
No, they engineered a structural solution using a TechMan cobot, a collaborative robot.
A collaborative robot, what's the difference?
It's a 6-axis robotic arm with built-in AI and machine vision, specifically designed to operate safely alongside humans without requiring heavy steel cages.
Oh, I see.
The author integrated this cobot into the line to handle the physical transfer of the explosives. The machine absorbed the risk.
That's incredible.
And the author explicitly notes that while the financial savings of that automation mattered to management, the ultimate metric of success was the message the factory worker sent home at the end of their shift.
I'm safe tonight.
I'm safe tonight.
The quiet architect calls this restorative engineering. The core belief that real technology does not exist to replace people. It exists to restore their safety and dignity. It guarantees their physical security and removes fear from the workflow.
That's the heart of it.
And the sheer spectrum of this mindset is staggering to me. The exact same rebellious engineering instinct required to clamp a logic analyzer onto a Siemens lathe in Pune is the exact same instinct used to protect a human in a grenade factory.
It's all connected.
It's all just about decoupling the iron from the brain to serve human needs.
And the author demonstrates how this philosophy scales to the highest possible stakes. They are currently applying these exact same engineering principles, bridging physical hardware with digital intelligence to the field of bioprinting.
Literally printing human tissue.
Yes. The mechanical principles are identical. You identify the structural bottleneck, right? On the factory floor, the bottleneck is the OEM protocol holding the iron hostage. In medicine, the bottleneck is organ failure or the critical lack of compatible human tissue for transplants.
So you intervene at the edge.
Exactly. The bioprinter uses a translucent hydrogel lattice, extruding cells through surgical-grade stainless steel nozzles with the exact same mathematical sub-micron precision used by the edge AI to control the lathe.
Wow.
You restore the biological system. You manufacture time for patients. You make, as the author beautifully puts it, hope tangible.
Hope tangible. It is an incredibly massive, life-altering vision. Yet the quiet architect grounds this entire philosophy with such a brilliantly humble detail at the end of their essay.
Oh, I know the one you mean.
They write, "My mother still thinks I fix printers. She sees the literal truth."
It perfectly encapsulates the quiet humility required for this kind of restorative work.
It really does.
The author heavily references the design philosophy of Dieter Rams, specifically the principle of less but better.
Rams.
Rams believe that good design is unobtrusive, honest, and strips away all non-essential information.
I look at the convoluted OEM protocols, the encrypted handshakes, the fatal system alarms, the intentional memory wiping, and it is the exact opposite of Dieter Rams.
It's anti-design.
It is artificial complexity. It is bad design because it exists solely to serve the manufacturer's profit margin, not the user's utility.
Exactly. By hacking the CNC controller with a logic analyzer, or by building a bioprinter to manufacture tissue, the independent engineers are stripping away that artificial complexity.
Getting down to what matters.
They are revealing the pure, functional utility underneath. They are reducing the system to its honest components, the indestructible physical iron and the open-source intelligence directing it.
So the goal, whether cutting aerospace aluminum or printing a human organ, is quiet, unobtrusive, highly functional impact.
Less, but better.
Let's bring this all together. We started today in the diagnostic muddy waters of global manufacturing, looking at millions of dollars of heavy machinery held hostage by synthetic software toll booths.
The artificial bottlenecks.
Right. We saw the legacy OEMs weaponizing safety protocols, willing to deliberately corrupt SRAM memory and paralyze machines just to enforce hardware obsolescence.
And we explored the rigorous diagnostic arsenal required to fight back.
The oscilloscopes, the BGA rework stations, the legacy RS-232 connections used by teams like Synchronix to carefully preserve data before the system destroys it,
We dissected the mechanics of the heist.
the Jugod to precision retrofits, using an automated tool change to force a massive coordinate data exchange, allowing a logic analyzer to intercept the encrypted handshake.
We saw how open source Edge AI perfectly spoofs those commands, decoupling the indestructible iron from the proprietary brain.
We looked at how startup founders use 48-hour validation tests on decommissioned machines as asymmetric bets to audit their hidden dependencies and ensure they actually own their factory floors.
Which flips the economic gravity.
Completely. And finally, we followed the quiet architect from a grenade factory to a bioprinting lab, realizing that restorative engineering is about stripping away artificial complexity to make hope tangible.
It is a remarkable testament to the power of open source intelligence and human ingenuity overcoming enforced obscurity.
So what does this all mean for you, the listener? Whether you run a machine shop, manage a tech startup, or just interact with a world increasingly locked down by proprietary software, I want to leave you with one final, slightly terrifying thought to mull over based on these sources.
Oh.
We know independent edge AI can successfully map and mimic highly complex proprietary handshake protocols, and we know the cast iron beds, the ball screws outlast its software by decades.
Right.
If an AI can eventually be trained to translate seamlessly between any legacy software protocol and any physical servo motor, are we approaching a near future where hardware brands cease to matter entirely?
That's a profound question.
Will the future factory floor simply be a mix-and-match graveyard of ancient, indestructible metal parts? A Fanuc lathe bed bolted to a Siemens spindle, driven by a Mitsubishi servo, completely stripped of their original software, and flawlessly animated by a single, invisible, open-source AI brain.
A Frankenstein's monster of perfect submicron precision.
Exactly. And if that happens, what happens to the multi-billion-dollar legacy OEMs when their invisible software moats just evaporate overnight? When the toll booth disappears, who owns the road?
Wow.
Something to think about, especially if you hold stock in legacy manufacturing. Remember, a perfectly good machine is only broken if you let the software tell you it is. Thank you for joining us on this deep dive. Keep questioning the control points in your own lives, keep looking for the hidden bottlenecks, and we'll see you next time.